Right now, at this very moment, a spacecraft 36,000 kilometers above Earth is staring directly into the sun. Not blinking, not resting, every single second. And what it's showing us has completely changed what we thought we knew about the closest star to our world. Because with our own eyes, the sun looks like a featureless ball of blinding light. But through the right lens, it becomes one of the most violent, beautiful, and mysterious objects in the entire solar system. Today, we're going deeper into the sun than ever before. For most of human history, looking at the sun was something you simply didn't do. And for good reason. Our eyes aren't built for it. In visible light, the sun appears as a smooth, glowing sphere. But that surface, called the photosphere, is actually just the sun's outermost visible skin. It's only about 500 kilometers thick, and it sits on top of layers we've never been able to see directly. Beneath that skin, hundreds of thousands of kilometers of churning, superheated plasma, magnetic fields powerful enough to launch material the size of Earth into space, and temperatures that defy logic, actually getting hotter as you move away from the core. But here's the problem. From Earth's surface, the atmosphere filters out most of the light that would reveal these hidden layers. To truly see the sun's deeper secrets, you need to get above the atmosphere entirely. And that's exactly what NASA did. In February 2010, NASA launched the Solar Dynamics Observatory, or SDO, into a geosynchronous orbit around Earth. This spacecraft is unlike anything that came before it. Its cameras capture an image of the sun every 12 seconds in 10 different wavelengths of light, most of which are completely invisible to human eyes. Each image is 8 times the resolution of HD video. That means, over a single day, SDO captures over 70,000 images of the sun. But the real breakthrough isn't just the quantity of data, it's the type of light SDO uses to observe our star. SDO primarily captures the sun in extreme ultraviolet, wavelengths of light far beyond what your eyes can detect. And when you look at the sun in ultraviolet, something remarkable happens. Different wavelengths reveal different temperatures, and different temperatures exist at different depths in the sun's atmosphere. By switching between wavelengths, we can literally peel back the layers of the sun, like looking through a window into regions we've never seen before. Let's talk about what SDO actually shows us. The sun's atmosphere has several distinct layers, each hotter than the last, which, if you think about it, makes no physical sense. Why would something get hotter the further you move from the energy source? That mystery is called the coronal heating problem, and it remains one of the biggest unsolved questions in astrophysics. But first, the layers themselves. The photosphere. This is the visible surface, around 5,500 degrees Celsius. This is where sunspots form, darker, cooler regions where intense magnetic fields suppress the flow of hot plasma rising from below. The chromosphere. Just above the photosphere lies a thin, transparent layer that emits a reddish glow during total solar eclipses. Temperatures here range from 6,000 to 20,000 degrees. The transition region. A razor-thin zone where temperatures spike dramatically, jumping from tens of thousands to hundreds of thousands of degrees in just a few hundred kilometers. We still don't fully understand why. The corona. The sun's outer atmosphere, extending millions of kilometers into space. Temperatures here regularly exceed 1 to 3 million degrees Celsius. And this is what SDO gives us an unprecedented view of. When we observe the sun at 171 angstroms, a specific ultraviolet wavelength, we see material glowing at around 600,000 Kelvin. We can watch enormous loops of plasma anchored by magnetic fields, arcing out thousands of kilometers into space. At 193 angstroms, we see material at over 1 million degrees, revealing the full structure of the corona and the dark patches called coronal holes, where the sun's magnetic field opens out into space and flings particles outward at extraordinary speeds. This is the solar wind. And at 304 angstroms, we see the chromosphere, the deep red layer that erupts into massive plasma tendrils called solar prominences, towering above the surface before either collapsing back or exploding into space as coronal mass ejection.